So now we will solve question 13. And it says that for this following circuit right here, find the values of all of these following things right here: voltages and currents and power and gain and all the rest. And it is labeled all on this graph here. So I have it currents labeled in blue that we need to find, and I also have this voltage that we need to find, which is labeled in this red. So let's start with the simplest one that we can solve here. We know that in an ideal op-amp, no amount of current can enter the ideal op-amp input terminals. So in an ideal op-amp, no current should enter at these two spots. So that makes solving this I in very easy. So the simple one is I in is equal to 0 amps. So we have solved for I in. Now, the next easiest, parameter to solve for on this circuit is that we know that in an ideal op-amp, so in an ideal op-amp, we know that ideally there will be a virtual short circuit across the input terminals of this op-amp. And that is due to the reason that the open loop gain ideally should be equal to infinity. Again, that's in the ideal case, but so taking that assumptions, we can know that due to short circuit approximation, this V1 is short circuited to this V in 1 volt. So therefore, V1, I guess that node is labeled as V1 is equal to 1 volt. So we have solved for V1. And then it's easy to solve for I1 because we know that this voltage now, and we know this ground voltage, and then we know the resistance in between, so we can solve for I1. So therefore I1 is equal to V1, which is 1 volt, minus ground with 0 volts, so just 1 divided by 1 kilo ohms, right? So then 1 divided by 1000, so therefore I1 is equal to 1 milliamps. Okay, so that is for I1. So it looks like we're just going in order now, so I'm guessing the next one to solve is I2. So so I2, as we can see here, no in an ideal op-amp, no current should enter the op-amp. So therefore, this I2 through here, it has to also then continue through the second part of the branch. So therefore, we know that I1 has to equal I2. And because we just solved I1 is 1 milliamps, therefore I2 also needs to be 1 milliamps. Okay, so that's I2, and yeah, we're going in order, it looks like. So V out is next. So for V out, we can observe that there is a current path, KCL, going from this voltage of V out through the resistances and then to this ground here. So therefore, it's just the voltage drop across these two resistances, which we know I1 is equal to I2, 1 milliamps. So we should just do V out, which is equal to the current there, which is 1 milliamps, and then so V equals IR, right? So with V equals IR is current is 1 milliamp, and then the summation of the two resistors in series is 1 kilo ohms plus 9 kilo ohms. So therefore V out is equal to 1 milliamp, which is just times 10 to negative 3, and then multiplied by 10 kilo ohms, and the kilowatt is times 10 to the 3, which cancel with the times 10 to negative 3. So therefore V out is equal to 10 volts. Okay, next they ask us solve for I guess it's called IL. So IL is defined by this current here. So that's pretty simple. It is just the voltage drop across that resistor is V out minus ground divided by 1 kilo ohms, right? So then it's IL is equal to V out, which we just solved, is 10 volts divided by I as resistance there is 1 kilo ohms, 1 times 10 to the third. So therefore IL is equal to 10 times 10 to negative 3, and we just shift over the decimal point in one, well actually let's just keep it in milliamps then. So IL is equal to 10 milliamps. So okay, the next one's I out. So I out is solved by KCL. So we do KCL at V out node, and the reason is because I said it wrong. So no, we have already solved I1, which is equal to I2. So we know this current here. We just solved for this IL here, so there's only one more coming in. Remember, this is the output of op amp, so I out. So how we do KVL is that if the current enters the node, there's a minus sign. If the current leaves the node, there's a positive sign. So I out is entering this node here, so it is minus I out. And both I2 and IL are leaving, so it is positive I2 and positive IL. And we know KCL, everything must sum to 0. So then I can say that I out is just equal to I2 plus IL, right? So then I out is just equal to, so I2 was 1 milliamps and IL was 10 milliamps, so 1 plus 10 is equal to 11 milliamps. Okay, so that is solved for I out. Next it says solve for voltage gain V out divided by V in. So we have both solved it, so just the gain is equal to V out divided by V in. We have both already. V out is 10 volts and V in, well, V in was given actually, it was 1 volt, so then the gain is equal to 10 volts. Okay, and then well actually the unit is volts divided by volts. It's a unitless dimension. Now just get in the habit of that we should get used to using the decibels unit for gain. So recall that you just can, it's pretty simple. The formula is 20 times log base 10 of the gain in the linear, which is 10 volts, so divided by volts. If you go to calculator, this is, so you, well actually we don't need calculator because we can see that this 10 is gone, right? So what's left is 20. So then the gain is in dB is equal to 20 decibels is the unit. Okay, and so we have solved for the voltage gain. And next let's solve for the current gain IL divided by I in, which both values we already have it. So that is just IL divided by I in. Now remember IL, we just solved it, it was 10 milliamps, but I in is 0 amps. And dividing anything by 0 is equal to infinity. So current gain is infinity. I guess the unit is amps divided by amps. So we have solved for this one. The last one is the power gain PL divided by P in. So I'm guessing that PL is referring to see, if this is IL, then I assume this voltage drop is that is VL, or otherwise known as V out, and then P in is, I'm guessing P in, the meaning of that is that you just do the current here is I in multiplied by the voltage 1 volts. So my guess is that power gain, I guess unit, okay, well, they called it PL divided P in, so then it's voltage, so IL is known, I'm guessing VL is referring to the voltage drop there, so it's V out multiplied by IL, and then P in is just V in times I in. Yeah, so it is V in times I in, which is so the numerator is V out is 10 multiplied by IL, which is 10 milliamps, and then the denominator V in, which is V in 1 volts, yeah, that was given, and then I in is a 0. so the power gain is equal to infinity, and we also have an ideal op amp, so that is not unexpected. Question 14, it says to connect a transducer that has an open circuit voltage of 1 volts and it also has a source resistance of 1 mega ohms. So we connect this transducer to a load of 1 kilo ohms resistance, and a question asks to find the load voltage if it is a direct connection. So I didn't understand at all what this question was talking about, but it turns out it was a very wordy question and is actually a very simple solution. And basically what it's saying is that we have a transducer, and the transducer really is just means it's called a sensor, right? So we have a sensor that has an open circuit voltage of 1 volt. So I assume it, and this is my assumption, I could be wrong, but when it has a sensor with a open circuit voltage, that means that when you don't connect anything to this sensor, you leave it as open circuit. Well, if you leave it as open circuit, then it should be 1 volt. That's what the question says. So open circuit voltage of 1 volts, and that's the meaning. So you don't connect anything to here. There's no current that passes through, in or out of this sensor. And so open circuit voltage would be 1 volt. And then it says that this transducer has a source resistance of 1 mega ohms. And I assume that source resistance, which is 1 mega ohms, is in series with the source, because in ideal sensor, it means that there should be such a strong resistance that it does not pass in or out any current which will affect the data measurement. So I assume on the sensor side it meant to say that this is a 1 volts of source voltage here, and then it has a source resistance in series of 1 mega ohms, and it's a very big resistance so that no current will pass in or out of this sensor. And then it says that we have a direct connection to our load. That's why I have this line here. So we have direct connection to our load, which tells us it's just a load that has a 1 kilo ohms load resistance. And the question is find the load voltage, which is just this equivalent voltage across this resistor here. So it's this very simple solve, actually. It is just, we can just use the voltage divider formula, which says that because VL is the midway point between two above this resistors here, So we know that the voltage divider formula, so the midway point, which is VL, is just equal to the source voltage multiplied by, in the numerator, we put the lower resistor, and then in the denominator, we put the summation of the two resistors in series. And we're told that Vs is equal to 1 volt. So it's just 1 multiplied by 1000 divided by, okay, 1 million plus 1000. So it's 1 million, 1000, 1 million and 1000. But so here is million, and then here is 1000. Like this, but you know, I don't want to use calculator, so we just you know, it's roughly equal to 1000 divided by 1 million. Okay, 3 goes away and the denominator just left with is 1 over 1000. So then we just say well, load resistance approximately equals to 1 millivolts. So part B, it is the question as to now we find what is the load voltage if it's through a unity gain voltage follower. So again, I didn't really understand what it was talking about, but I think I have some inclination on what is going on here. So first of all, a unity gain voltage follower, actually a better name for this is buffer. So a buffer is because that there is no gain on this circuit. We don't have any resistance in the feedback path, and we don't have any resistance on the input side either. So this is just, well, in this unity gain voltage follower, is V out is just equal to V1 times V in. Is unity gain, means the gain is 1. And the question asks, find out the load voltage if it's through a unity gain voltage follower. So we will use this instead of the sensor in part 14a. So let's make the approximate circuit equivalent here. We know that a better way to model this is V in is here, and we sample this voltage from V in to, well, I guess ground, right? And that is V in, and then we instead model this as a voltage controlled voltage source. So it's with the gain of 1. So it's 1 time unity gain. So gain of 1. So 1 times V in, and then we defined all the way up here as the output. Something like this. So the question is saying that now, instead of using the sensor from the previous problem, now let's use this unity gain voltage follower as our new sensor, or in this case, they use this terminology, they call it a transducer, which converts some kind of signal into electrical signal. So what that just means is we use this as our sensor now. So I'm going to copy and paste it here. And now we attach our same load to our to the sensor. So remember, it was the load resistance which was 1 kilo ohms, and then same thing, just the output of the first part just connected to this new sensor that we have. Now keep in mind that there is another thing that we need to add to this circuit that we just drew here. Is, remember, there was a statement that said that there is a source resistance of 1 mega ohms. So right, so now, well, actually let's just copy this sensor part of it, and then we connect that. But before I do that, let's slide it to the right to make some space, and then let's connect this sensor part of it to the V in. Right, so this is our new circuit, and solve for this is called VL now, and let's solve for VL. So everything the same almost, basically. So again, there is no current that flows through here, so all the way up until this point here at the very end it's still 1 volt. It does not matter that we have a source resistance. Okay, so 1 volt is the sample point, so it's 1 times 1 volts. So VL is equal to 1 volt. So VL is equal to 1 volt here.